Yes,
written
yes,
notes? Okay, fine.
yes, yes.
So, yeah, let's today. Um, it appears that Professor Rajendra is not here today. I just had a discussion with him, and he said that he'd be joining late, a bit late. So, okay,
Yes.
so
So he
I
will
shall then.
join sir at 3 o'clock. I will be here till 3. Don't worry. We
Okay,
are
fine,
here with you. Yes.
fine. All right. So today, the basic plan is that first there was a question that Professor Rajendra sent last evening regarding some point that had been discussed earlier in the course of the second day. So I shall first answer that question, and then there are few small points to discuss, and then once having done that, what I shall do, that I mean, the plan for today is that the first I shall address the question raised last in the last session. Then I shall discuss a few pending points in from these notes pertaining to polarization, and after that, I will round up the course because today is the last day of this course, for 1 hour, and then I shall try to connect all of these ideas to some basic principles of quantum communication. So that is the way I have planned everything for today. So before I start, I hope that everyone can hear me clearly and see the notes clearly. So if it would be helpful if you could please confirm it once again, any one of you, madam.
Yes, yes.
Okay.
Thank
Thank you very much for the confirmation. So let us begin. Yesterday we finished the last, I mean, one important topic on optical polarization, and that is optical activity. And we discussed Fresnel's theory pertaining to optical activity. It is a phenomenological theory without getting into too many details. And today I shall start the discussion on the topic of specific rotation. This will be the last topic. But before that, I would like to take up the question that was raised by one of the participants. Then this question was forwarded to me by Professor Rajendra. So the question is that how is it possible that wavelength changes but frequency remains the same? Are they not reciprocal of each other? Is it something in relation to the medium through which light is propagating? Well, let us first address the first question. So, are since wavelength and frequency are reciprocal of each other, should they not change when, or should the other not change? If should, in the event that one changes, should the other not change? Well, that can happen if the velocity is fixed. For instance, in the case of light, the speed of light is a universal constant. And so, if you change the wavelength, the frequency shall change along with it also. However, if the velocity itself changes, such as happens to light when it moves from vacuum and enters a medium, then in that case, what are we to make of it? If the velocity changes, noting that the phase velocity of a wave is the product of the wavelength and the frequency of the wave, then in that case, if the velocity itself changes, then what should change on the right hand side of that equation? The wavelength or the frequency or both? So the answer to this is given in quite simple terms in the book of Jenkins and White, Fundamentals of Optics. I mentioned to you on the first day itself that these notes that I have prepared are based on the two books. One is Fundamentals of Optics by Jenkins and White, and the other is Optics by Eugene Hecht. So here is, I'll read out a few things from Jenkins and White to answer this question, that are they not the reciprocal of each other? Should wavelength change? Should the frequency not change? Well, here, so this is from Jenkins and White, chapter 11, section 11.10. I mean 11 dot 10. chapter 11, section 10. The title of this section is Frequency and Wavelength. So it says that I'll read out. So any wave motion is generated by some sort of vibrating source, and the frequency of the waves so generated is equal to that of the source. So if the source is vibrating, that is, so if the source is oscillating, then the process of oscillation will generate a wave, and the frequency of the wave will be equal to the frequency of the source itself. So the wavelength in a given medium is then determined by the velocity in that medium, and by dividing the velocity by the frequency. Of course, velocity is equal to frequency into wavelength, so wavelength will be equal to velocity by frequency. So you can see immediately that the frequency of a wave is connected to the frequency of the oscillating process that created the wave in the first place. So it is not so easy to change the frequency. And it's not, I mean, one has to be a little careful when one says that. So passage from one medium to another causes a change in the wavelength in the same proportion as it does in the velocity, since the frequency is not altered. So as light, let's say, or any other wave that moves from one medium to another, then the frequency of that wave is not altered. It is the velocity that is altered, and the wavelength that is also altered accordingly. So v is equal to f into lambda. The frequency remains fixed, and so correspondingly, if the velocity changes, only the wavelength will change. Now we address the question of why only the velocity, why the velocity, the wavelength should change. Let us see now, and the frequency should not. So here's again the discussion from Jenkins and White. If we remember that a wavefront represents a surface on which the phase of motion is constant, it should be clear that regardless of any change of velocity, two different wavefronts are separated by a certain number of waves. So you take two wavefronts in this propagating wave, and the wavefronts will be separated from each other by a certain number of waves, and the number of waves accommodated between two wavefronts will remain. It's a number, and this number will remain fixed regardless of the medium uh, into which the wave is propagating. That is to say, and the number of wavefronts that one accommodates between two, the number of waves that one accommodates between two wavefronts is the actually connected to the frequency. And so if the number of wavefronts is not changing, so that is like, let's say that we are counting the number of wave crests between two wavefronts. That number is not changing, and that is also a representative of the frequency of the wave. So that will not change. So here's a very clear argument over there. So that is, the length of any ray between two such surfaces is the same. So now, what happens over here is that we are now talking in terms of a ray instead of a wave. So basically, a ray is associated with geometrical optics, not with physical or wave optics, right? Nevertheless, it's helpful. So the length of any ray between two such surfaces is the same, provided the length is expressed in wavelengths in the appropriate media. Now, very clearly, we come to the idea of light. As applied to light, the last statement is equivalent to saying that the optical path is the same along all rays drawn between two wavefronts. So now let us uh, discuss this thing in slight detail. So you have two wavefronts, let's say in vacuum, and between these two wavefronts, you have trapped a certain number of waves, as you can count through the wave crests, let's say. Now, this number of wave crests or number of waves is spanning a certain length, and the corresponding optical length. We are still talking about vacuum. The wave is propagating through vacuum. So the corresponding optical length will be the refractive index of vacuum, which is 1 multiplied by the geometrical length. So it is actually exactly the geometrical length. But as soon as the wave enters a medium, The frequency remains unchanged. Why? Because the number of wave crests between these two wave fronts is still will still have the same count. That is a representation of the frequency that will remain fixed. So what will change instead is the geometrical path. Let us now try to see. The optical path will also remain fixed, which means that once a wave enters the medium, the optical path between the two wave fronts will be the refractive index of that medium times the geometrical length over which these waves have been spread out between the two wave fronts. So effectively, it is refractive index of vacuum times the length of between the two wave fronts in vacuum. 1 into that length is equal to refractive index of the medium, let's say glass or water, so times the geometrical length. Naturally, the geometrical length will be reduced now because refractive index of a medium is more than in a material medium than in vacuum. And so the physical wavelength, not the optical path, but the physical distance over which the waves have been spread, that will be reduced. And so effectively the wavelength will be reduced, the frequency will remain the same, correspondingly the velocity will be reduced, and as such the velocity will become equal to the speed of light by the refractive index. So effectively it is like saying speed of light is equal to refractive
Sir,
index times, yes, someone is asking
sorry.
this.
Yes. So, um, your slides are not changing. Are
No, I'm not.
you answering? Yes,
Yes,
I think
yes,
so.
I'm discussing a different matter.
Yes.
I'm answering a question from the previous day, so with reference
Yes.
to
Yes.
with Jenkins and White. But you've been able to hear me, I hope.
Yes. Yes. So actually, I was also confused by seeing the. Yes, I understood that you started with that you will give the answer, but
Yes, yes.
seeing the audience, so I thought I will confirm.
No, no,
Yes.
no.
Thank you. Thank
Is the audience confused about this point? I hope not.
you. No, no.
Okay.
They are thinking that you are not changing the slide. So I thought I will confirm from you.
No, no,
Yes.
I'm not changing the slide because the answer to the previous day's question is not contained in the slide.
Yes.
Right. It
Yes.
is.
Yes.
It
No. No.
is. I'm reading out from Jenkins and White, section 11.10. Right.
Okay.
So it's so that so anyway, that is the answer to the question from the previous day. I hope it has satisfied the participant who asked that question. Now let me resume the main discussion on polarization. This is the last topic in this course that I shall take up, specific rotation. Yesterday, I hope all of you will recall that the last topic we finished talking about at the end of our 2 hour session was optical activity. So, this is connected to that specific rotation. So let's now try. So specific rotation is a measure by which you measure the make sense of the optical. I mean the strength of the optical activity of a substance. So let's try to see now. So let's look at this thing. Liquids consisting of an optically active substance, such as sugar, and an inactive solvent, such as water, they produce a rotation of the plane of vibration. So the rotation angle through which the plane of polarization will be rotated will be in proportion to the concentration of the optically active substance. So grams of active substance per cubic centimeter of solution. So that is C, concentration, and I have mentioned that point once again. I hope all of you can see that this c is not to be confused with the speed of light in vacuum, right? So the angle of turn through which the plane of polarization will be rotated through, you have let's say a horizontal tube of sugar solution, and you have made a polarized beam of light to enter this tube, and as the light passes down the length of the tube, its plane of polarization will start rotating. Uh, Before it entered, it was frozen in space at a certain orientation, in a certain state of orientation. And as it, after entering, it starts rotating. And then once it emerges at the other end of the tube, again, its orientation will be frozen in space. Okay. So the rotation angle will be in proportion to the concentration and also the length of the liquid through which the light has to travel or traverse. So theta is proportional to the length and the concentration. And so theta will be jointly proportional to the length and the concentration. And the proportional constant is S, and that proportional constant is known as specific rotation. Okay. And L is in centimeter, C is in gram per cubic centimeter, but we have introduced 10 over here because sometimes if you take it in centimeters, the number can become very high. Therefore, the length is reduced to decimeter unit, meaning 10 centimeters make a decimeter. So why this unit? Because I just touched upon the answer that there's a substantial rotation that happens at times, particularly with solid crystal material. Although in liquids also you have a reasonable rotation, we shall just refer to some numbers. So here we have specific rotation. So specific rotation, note please that it's a constant quantity. It's a constant of proportionality. So different substances will have different specific rotation values. So here, I think typically for sugar, it's a few, I mean, for some, a few degrees, 30 degrees or something like that. Okay. So let's just see for liquid material. Like in turpentine, the angle of turn for 10 centimeter liquid through which light is traveling, it is minus 37 degrees. Minus 37 degrees as in levorotatory. Note that we are referring to Fresnel's definition. If it's a negative angle, then it's a levorotatory material. If it's a positive angle of turn, and positive means clockwise, be a little careful on this particular point. When we measure angles, positive angles are anti-clockwise and negative angles are clockwise. But Fresnel's convention is quite the opposite. Clockwise angles, that is clockwise rotation, dextrorotatory rotation, is assigned a positive sign, and the opposite for levorotatory. Levorotatory is actually anti-clockwise. That should have a positive angle, but according to Fresnel's convention, it is negative. Okay, so here it is. So you can immediately see the turpentine is levorotatory with minus 37 degrees of rotation for 1 decimeter of liquid tube, I mean, liquid column. Okay. 1 decimeter of quartz is, yesterday, I hope you will remember my mentioning to you, quartz is optically active in the in the solid phase, in the crystalline phase, but not as a liquid. I think I mentioned it somewhere here. I mean, okay, I mean that's there anyway. So if you have crystalline quartz, uh, the turning angle you can see is a very large number, 2172 degrees. I mean, you'll have to subtract several factors of 360 degrees from this to come to the actual measured angle of turn on a circular axis. um, you have both plus and minus signs, meaning that there are two isomers of quartz, one left-handed and one right-handed, and accordingly, depending on the kind of crystal you have chosen, you'll get a plus rotation or a minus rotation. So sometimes the rotation is so large that you actually have to alter your definition of length down to a millimeter. But crystals are, of course, dense, closely packed, neatly ordered systems, as opposed to liquid. In liquid, the rotation is not a very substantial number as compared to what you can get in crystalline form. Okay, so now we just have a few points to discuss over here, and then we can conclude this part of the polarization notes. Okay, so isomers, I mean, same molecular formulae, but difference in structure. So, like I mentioned in the case of quartz, quartz has got a the molecular formula of the two isomers may be the same, but one will be left handed and the other will be right handed, which is to say that there will be a difference in their structure, the crystalline structure, and accordingly, you will have dextro-rotatory behavior or levorotatory behavior. Then racemic acid appears optically inactive, but it appears optically inactive not because it is an inactive material, but it has equal proportions of right and left-handed isomers. So there's a cancellation at the end, right? So these are optical stereoisomers. A good deal of chemistry, of course, goes behind all of these things. There's the name of the great Louis Pasteur in finding out all of these things, stereochemistry. And just to touch upon the biological implications of optical activity, although I mentioned this thing yesterday, but I'll conclude on this particular point. Glucose, sugar, dextrorotatory. And so, natural sugar, that's why it's called dextrose, is always right handed. You will not find left handed sugar naturally occurring. You can manufacture left-handed sugar in the lab. Probably you can give it the name Levos or something like that. But sugar is always dextrorotatory if you have to get it from nature. Amino acids are left-handed, almost always. But as mentioned over here, certain antibiotics have some right-handed amino acids. So probably, I mean, you would have thought that why should there be a distinction between left-handed behavior and right-handed behavior? I can't give you an answer to that. But these are biological systems. It has undergone a long evolutionary trail. There's a long evolutionary history, and somewhere probably one sort of handedness had a natural advantage over the other sort, given the circumstances prevailing at that time, and so natural selection worked at selecting that particular handedness, and the other was slowly phased out of the biological pool. So, probably that. Anyway, so that's up to page 50. We have finished. Now, let's quickly just skim through the rest. These are not really very relevant for this course because these are just some. See, actually, these lecture notes that I prepared, they are quite old, and so when I wrote them, I never thought that one day these will become relevant for uh, quantum communication. So I just added a few things. So I will not discuss these things. I'll just skim through and I mention a few things. Polarimeters, measuring devices to find this polarization state. There are two types of polarimeter. You have a half plate, half shade polarimeter over here. I mean, one part is a birefringent material and the other part is glass. Then you have a bi-quartz polarimeter made of quartz, left-handed quartz and right-handed quartz. Beautiful colors you can see. I have worked with all these things in the lab at some quite a long time ago. I remember those experiments. And then some discussions on polarimeters, the two respective kind of polarimeters, and some basic theory. But these are not really relevant for your material. They're just part of the notes packaged. So you may go through them if you feel like, but they are not, as I mentioned, they're not really very relevant for from a quantum communication point of view. So what I shall do now is to take stock of what we have covered in this course. And then I shall try to connect all of these points, the salient points of this course, with some basic ideas of quantum communication. So let us quickly go back to where we started in these notes. So, okay. So I hope all of you can see the notes. One of you could please confirm. We are going back to.
Yes, sir. Yes,
Yes,
sir.
yes. So you are able to hear me and also see what I'm projecting. So let's just look at what we have. So I have covered something like 50 pages of notes over the last 2 days and half of today. So nearly half an hour has gone by. So these notes up to page 50 can be divided into four broad categories. Let us see. Page 1 to page 10. Page 1 to page 10 are some basic ideas of observational, phenomenological ideas of polarization, right? Covering wave nature of light, basic concepts of polarization, Malus law, Brewster's law, polarization by refraction, as you can see, all up to here. So, page 1 to page 10, you have the basic ideas, concepts of polarization. Page 11 onwards, page 11 to page, so that's the first chunk, page 1 to page 10. Then page 11 onwards, we start discussing double refraction, that is birefringence, page 11 to page 22. So these two chunks were covered on the first day in the 2 hour session. So page 11 to page 22, we discussed double refraction, uh, a unique phenomenon in pertaining to certain crystals and polarization itself. So that's the second category, birefringence or double refraction. Then, so that was on the first day, which was Monday. Then page 23 onwards, page 23 onwards to page 36. Let us see. Page 23 onwards to page 36, we covered superposition of orthogonal waves and how polarization is achieved through the superposition of two orthogonal electromagnetic electric waves, electromagnetic waves, whatever you want I mean, although we haven't referred to magnetism here, but be it understood that as soon as we talk about electricity, magnetism is locked in space alongside the electric field vector. So any one of them would do. We have chosen electricity. So up to page 36, we have discussed superposition of two orthogonal waves, and then depending on the phase difference between the two waves, what sort of polarization states you can achieve: plane polarized, elliptical polarized, circular polarized light. And elliptical and circular polarized light will differ from each other due to the difference of the amplitudes of the two orthogonal waves. So that, and then how you can practically tune these states with the help of retarder plates, full wave plate, half wave plate, quarter wave plate. Yesterday we discussed that. So that was the third chunk, going from page 23 to page 36, right? Circular polarization. And then the last chunk, fourth chunk, starting from page 37 to what we concluded today up to page 50. This is optical activity. And alongside optical activity, we discussed the ideas of dextrorotatory behavior, levorotatory behavior, and most importantly, Fresnel's phenomenological theory of optical activity. And today, we just extended that little discussion up to page 50 for, I'm sorry, just a minute, for the idea of specific rotation, as you can measure optically active solutions or any optically active substance, even crystal substance, in the laboratory. So different kinds of optically active behavior will be captured by different specific rotation values, which is a constant for a particular material. Okay, so with these four chunks, we have concluded the discussion on polarization as it would as one could relate it to some basic points for quantum communication. I shall now, in this last half an hour remaining, discuss those ideas. So, first of all, what is it that we have addressed in our course so far? We have addressed two broad questions. One is, what is polarization? That's the first question. I hope all of you are able to understand what I'm driving at clearly. This summary of whatever we have discussed with the help of these 50 pages of notes. The first is the question of what is polarization, And the second is how to reduce, I'm sorry, how to produce or measure polarization. So that is the second question, how to produce and measure polarization. So those are the two broad questions we have addressed in our course so far. Now, what we shall do is to connect these ideas to some basic concepts of quantum communication. Of course, as I mentioned to you yesterday, and today I shall reiterate that point, that my knowledge of quantum computing is not very extensive, I'm afraid. So I can't really go into fair detail. So I shall just have a little discussion with reference to polarization from the book of Nielsen and Chuang, Quantum Computation and Quantum Information. Once again, I shall remind you that my knowledge of quantum computation doesn't go too far, I'm afraid. However, I mean, my mandate in this course was to discuss basic concepts of polarization and then at the end of it, build a bridge with quantum computation, quantum information, perhaps quantum communication, and then experts in the domain will take the matter forward. So let us see what is it, how is this whole idea of polarization relevant for quantum communication. So, two words, quantum and communication. So, I am reading out a passage from Nielsen and Chuang's book, Chapter 1, Section 1.2. This is a standard book on quantum computation globally. So, I hope you are aware of that and you can just refer to that. So, let's now see what we have over here. So, first, let's just look at the whole idea of computing. What is computing based on? Computing is computers are based on the idea of a bit, 0 and 1. 0 pertains to, let us say, the absence of an electrical pulse, and 1 pertains to the presence or the passage of an electrical pulse, a current, very simply put. So you have these two 0-1 states. I'm talking about a normal computer, not a quantum computer. A 0-1 state, you have these two 0-1 states, and all information could be stored or processed as a sequence of these of this 0-1 state. Different sequences will happen over here. So these 0-1 states, 0 and 1, they are known in normal computing parlance as a bit 0 and bit 1. Now, in quantum computer, that idea is extended to qubits. QU, then bit, bit. QU as in quantum. So effectively, it's a quantum bit, qubit. So these quantum bits in notational form are like in Paul Dirac's bracket notation, ket of 0 and ket of 1. Effectively, it's a wave function. In quantum mechanical terms, it is a wave function. One wave function stands for the 0 state, and another wave function stands for the 1 state. I am not referring to any notes over here. So please don't be confused that I'm not showing you any notes. I'm just talking about it from a way. It's so basic that I don't think notes are necessary. It's just in the second section of the first chapter of Nielsen and Chuang's book. But the major difference between a quantum computer and a normal computer is the following, that in a normal computer, there is no superposition of the 0-1 bit. The 0 stands separately in its own right, and the 1 stands separately in its own right, and they are not mixed with each other, they are not superposed with each other. But in quantum computers, the 0-1 bits, or the qubits, I'm sorry, the 0-1 qubits can be superposed. And this is the key difference, key feature of quantum computing. All the anticipated or expected computing power, storage power, high level of memory processing, all of these things are based on this superposition principle between the two bits, the qubits, I'm sorry, once again, qubits, 0 and 1. Now, how they, how it increases computing power, processing, and memory, and all of these things. An expert, no doubt, will be able to give you much better insight into these questions. I'm not that expert. However, now that I have mentioned this thing, how does polarization fit into this picture? Polarization of light. Let us see. And this I am reading out now from Nielsen and Chuang's book. So it's in the, as I said, section 1.2. So to get a concrete feel for how a note that, qubit can be realized, it may be helpful to list some of the ways this realization may occur, as the two different polarizations of a photon, as two states of an electron orbiting an atom with its plus one spin up, spin down state. So there you have got two quantum examples properly from physics. So two different polarizations of a photon and two different states of an electron, like spin up, spin down state of an electron. But I shall not refer to electrons anymore. I shall go straight into the idea of a photon and its polarization states. So basically, uh, you are now talking about a photon with polarization. Be a little careful when you apply this term. Polarization is not a particle phenomenon. Polarization is a wave phenomenon. Light is an electromagnetic wave, and as such, light shall display three wave like features, three properties that always go with waves, namely interference, diffraction, and in the particular case of light, electromagnetic wave, polarization. So, polarization is a wave like behavior, a phenomenon. Nevertheless, you can associate polarization with a photon. Note that photon is no longer a wave, a photon is a particle of light. But you can take the liberty of going from the wave picture to the particle picture through wave particle duality. So, although polarization is strictly formally to be associated with the wave like behavior of light, you can still, because of wave particle duality, because light is both a wave and a particle, we discussed this thing in the course of one question that was raised in the first day's session, that light can be both a wave and a particle, and the particle of light is known as a photon. So the polarization of light, which ideally should be associated with the wave character of light, can also be extended to the photonic character of light, or the particle character of light. So you have got two different polarizations of a photon, and this will help you in framing what you might call a photonic qubit. Let us see how. In these notes, you can go to, although these notes pertain to very, very basic ideas of polarization, nevertheless, you can still see some features of that. This is in the third chunk, which we discussed yesterday. Superposition. We talked about superposition of two orthogonal waves, right? So here it is that you have got two electric wave, EX oscillating, electric field oscillation, electric field oscillation, EX oscillating along the x-axis, EY oscillating along the y-axis. And then you can carry out a superposition of these two phases. Of course, there is a phase angle different. A superposition of these two waves. Of course, these two waves have a phase angle difference between the two of them, and then tuning the phase angle difference, you can produce various sorts of polarization states. Like, for instance, if the phase angle difference is an integral multiple of 2 pi, you'll get a linear state of polarization trapped in the first and the third quadrant. If you have an integral multiple of pi, then you'll have a polarization state trapped in the the second and the fourth quadrant. If However, you have an integral multiple of half, or rather, if you have a phase difference of pi by 2, then you will have a state of elliptical polarization. And then when the amplitudes are equal of each other, of the two waves, mutually perpendicular orthogonal waves, then you'll have a circular state of polarization. So you can produce all sorts of polarization states. And how you can produce them? You can produce them by making them pass through retarder plates. Yesterday we discussed that. So a photon, but please just note that these equations that I have written over here, they pertain to a wave, not a particle. Nevertheless, light is a particle through wave-particle duality. So the polarization state can also carry over to the particle picture of light. And these two polarization states, let's just go back to our simple diagram here. These two polarization states, let's say Ex and Ey, can stand for your two photonic qubits, one 0 and the other 1. And then the superposition, I'm just talking about a 2-qubit system. And then the superposition of these two qubits can be tuned accordingly through the phase angle difference. So this is one case where you can have two polarization, two photonic qubits, bringing about some sort of a superposition, and the basic idea of quantum computing is satisfied. Then there is also another case, what we have here. Yesterday, when we discussed optical activity and Fresnel's theory, Fresnel himself established, gave a phenomenological theory for optical activity. He lived 200 years ago. He could not have imagined that this could be relevant enough. I'm sorry. The mic just dropped off. Can you please confirm that you can hear me? I'm sorry.
Yes, yes, we can hear
Yes.
you, sir.
Thank you for the confirmation. So the previous example that I discussed of two photonic states, or two 0, 1 qubit states, were two linear waves, mutually perpendicular to each other, orthogonal linear waves. And then you can have two waves whose linear superposition can be produced also to produce, can be worked out also to produce different kinds of polarization: circular, elliptical, linear, whatever you want. But then the other thing is the reverse is also possible. Yesterday we discussed, that is, linear polarized light is a superposition of two states of circular polarization. So in the previous example that I referred to, you have got two linearly polarized light, and their superposition can bring about circular polarization when you have a phase angle difference of pi by 2. Negative pi by 2 will give you right circular polarization, positive pi by 2 will give you left circular polarization. But the opposite is also true. Linearly polarized light is a superposition of two circularly polarized states. So these two circularly polarized states can also stand for your photonic qubits. One will be 0 and the other will be 1, and then you can produce the superposition of these two. Note that superposition pertains only to quantum phenomena, and quantum computing is very much a quantum phenomena. You will not get superposition in your normal computer, right? So that is one thing. So you can, I have just referred to these cases where you can produce superposition of 0, 1 qubit states, and the 0, 1 qubit states can be achieved with the help of the different kinds of the two polarized states of polarization, two different polarization states of a photon, once again a particle, but wave particle duality can allow us to connect polarization with this particle like behavior. Otherwise, classically speaking, polarization only goes with a wave, not a particle. Okay, now the thing is that how can you produce polarized states? I mean, you can do it in so many ways. Yesterday and the day before we have discussed. Let us just go back to the second chunk in our discussion, the second topic, double refraction by refringence. So here is a situation uh, where you can see this thing. You can create a separation of the E rays and the O rays. Natural light with a certain polarized state has been made incident on a calcite crystal, and then the light has been split into two polarized states. One is the extraordinary ray, which contains polarization on the plane of the paper, and the other, I think those are called p, that is called p polarization, and the other is the ordinary ray, whose oscillations are normal to the plane of the paper. Viewed head on, the oscillations will look like dots as they enter the page, right? And you can clearly separate them with the help of a Nicol prism, which we also discussed, that you make light incident on a Nicol prism, and the ordinary ray undergoes total internal reflection and comes out here, and the extraordinary rays barrel through straight away and move on, and there you have a clear separation between these two states of polarization. So this is an example, a very simple example of a polarization beam splitter, that a beam has come and then it has been split into two states of polarization, and then the two states of polarization have been split from each other completely and segregated. So that is one way in which you can attain polarized light. And then of course, as discussed, so this is with respect to the double refracting behavior using Nicol prism. And then also yesterday we discussed half wave plate and quarter wave plate. With a half wave plate, you can create a phase difference of pi. And so, sorry, here, this is for a full wave plate. This is a half wave plate. And so you can create a phase difference of pi and create linearly polarized light. With a quarter wave plate, you can create a phase difference of pi by 2 and accordingly produce elliptically polarized light or circularly polarized light. And so, as you can see, the two broad questions: what is polarization and how can you produce and measure polarization? So these two questions have been fairly addressed, I hope. And then these can also be connected to quantum computing through the photonic idea of photonic qubits. A photon is the repository of two qubits, a 0 qubit and a 1 qubit. And each qubit will pertain to one particular state of polarization. When you have circular state of polarization, one going to the left, right turning polarization will be 1 qubit, and the other going to the right will be the second qubit, and their superposition will produce you for you linear polarized state or linear light. And that is the theory that Fresnel gave you. So all sorts of possibilities are there. Now the question is that I mean, you can have qubits or you can have quantum computing with the help of electrons also, because electrons also show the same behavior. An electron can have a spin up state and a spin down state. And spin up state can be 1 qubit and let's say 0 qubit, and the other can be 1 qubit 1. And then you can have their superposition. Quantum systems can superpose very easily. So, I mean, if you can do it with electrons, then why should you? I mean, what is the special benefit of a photon? Well, there are some special advantages of using photons. First of all, this QDP relates to quantum computation. I'm sorry, quantum communication. So, communication is best done or done at its fastest at the speed of light. That is to say, by sending photons, right? So, there you can see. So, if you want to send information in qubits, then and at the fastest possible, then of course the natural candidate is a photon, and the information in the photon can be contained in its two polarized states, 0 1 qubit state. There is also a further advantage. So, for instance, with photons, that is light, you can produce high levels of coherence. You can convert ordinary light to laser light, a laser beam. Incidentally, that will bring in the other phenomenon pertaining to the wave nature of light, namely interference. Interference, I mean, the idea of coherence is intimately connected to interference. And so you can produce highly coherent laser beams, and these laser beams can be polarized to produce your photonic qubits. So that will give you coherence, it will give you speed, the fastest possible speed, and light is also much easier to produce than control and work with than an electron, because an electron has a charge, and as such suddenly it can be affected by neighboring charges here there. So things could be safely or without or with less trouble, you can send signals through light. But of course, note one thing: electrons can also serve the purpose of optics, light at times. For instance, in the case of an electron microscope, you can see things with a much greater precision and for much less trouble than a photon. Uh, a normal microscope uses light, that is to say, uses photon, right? But an electron microscope uses an electron, exploiting its wave nature of electron, whereby you once again refer to the third wave phenomenon, namely diffraction. So it is not that there are conspicuous advantages always with a photon over an electron. Electrons can also serve their role, but as of now, with particular regard to quantum communication, I would say that those were the advantages of an electron. I'm sorry, a photon over an electron, namely that photons can be made highly coherent through a laser, and by making it laze, and then photons also have very high speed. I mean, the fastest possible speed in the universe. And so, if you convey information in terms of photonic qubits by exploiting their polarizing properties, you would have achieved much in terms of quantum communication. So I think I have been able to build that bridge with quantum communication. I believe this, I haven't got any notes on quantum communication to talk about. Anyway, these are very basic ideas. In standard textbook of any quantum computing standard textbook will discuss all these things. So you can refer to the first chapter itself to get these ideas. I have referred to Nielsen and Chuang's book. So I believe that this session has been recorded, so that last half an hour part where I discussed the the relevance of polarization to quantum communication is contained in that last half an hour part. So you could listen to them later and see for yourselves how much relevant it is, the whole idea of polarization with quantum communication. So I think I have nothing more to say. If there are questions, perhaps we could take those questions now. I will try my best to answer those questions. Hello, I hope you have all, madam.
Yes. So let me check the sir. Any questions are there? Uh,
Professor Rajendra has come. Has he joined?
I think he will be joining soon. Maybe he has
Okay.
a class till 3. Yes.
Okay. Fine, fine. You may please look at the questions and see if I can
Yes.
answer some questions.
Okay. So okay.
Hello.
I think few questions are. So they want to. Somebody is asking that is it possible to stream the experiment? I don't know which experiment he's saying.
What experiment?
Can you clear? So he has just wrote that. Is it possible to stream the experiment? Can you, Yarish Vami, can you please explain which experiment you are talking about? Can you write it again?
Okay, fine, fine. So while he writes, you may move to any other question while it is
Yes,
still
yes,
there.
yes. Okay, so another question by Vinod is, please tell that electromagnetic field theory and optics, they are follow the classical approach or quantum approach. Kindly tell this. Oh, they are asking.
Electromagnetic, I
Yes.
mean, for instance, standard electromagnetic that we have, that we read, let's say David Griffiths' book, that is very much classical. See, as long as something does not contain H, Planck's constant, that is, it's classical. Very simply. In polarization, nowhere have I referred to H, because it's a wave like thing, right? So as soon as I talk about a photon, immediately it becomes quantized. But nowhere in these notes have I talked about, have I mentioned photon. So these notes of polarization and the electric field oscillation, electric field oscillation, those waves, these are all very much classical, right? Hello?
Yes, sir. Yes, yes.
Yes, yes.
So another question is, can you comment and explain recent achievement of 1 kilometer transaction quantum communication?
No, no, I'm afraid I have no idea. As I said, I mean, my knowledge of quantum computation of these things
Yes.
is quite challenged actually.
Mm.
So perhaps you should pose this question to domain experts, those who have worked in
Yes.
the area of communications, optoelectronics, all of these areas. So I suppose in this FDP there will be some domain experts in those areas too.
Yes.
So
Yes.
yes, 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 madam.
Okay, I think then there is no the other question, sir. The similar
So,
question we are. Yes. Thank you. Thank
so
you very much, sir,
thank you.
for
But
this nice.
someone had that question on experiment. Has he been able to, or she been able to
Um,
clarify the question? Not yet.
yes, he wrote polarization experiments.
Yes, but what polarization experiments? Like I mentioned to you, most of the, see, the basic ideas will always relate to this working with plates and polarized polarimeters and all of these things. So at the end of the notes, beyond page 50, there are some of these experimental apparatus and all those things mentioned, but I thought that they wouldn't be quite relevant for the basic principle of this course, which is to actually connect it to ideas of quantum communication and quantum computing. So that's why I did not go into too many of those details, but you could look at anyway the experimental business about polarization and all of that you can find in the book of Jenkins and White and Eugene Hecht. So I mean they're nothing very difficult anyway. Yes, madam.
Yes. So, sir, this is just my request that you have already made a very good notes. If you can wrote down somewhere at the end that the name of the books you are uh, telling.
Uh, Actually, I gave the names to Professor Rajendra.
Then we can.
Fundamentals. Yes, yes. I sent the names to Professor Rajendra. Fundamentals of Optics, Jenkins and White.
Okay.
Jenkain.
I have
Yes.
already posted it on Canvas.
Oh,
Okay,
then
okay.
So
So
that's good.
the
then
Canvas through which we are sharing the lecture materials, I have posted the details of these two references which are
oh
used in these notes.
yes,
Okay.
yes, yes, yes.
Very good.
Fine.
Thank you.
That is
Yes.
Jenkins and White and Eugene Hecht. I think
Yes.
Hecht has got an Indian partner these days. So I mean co-author.
Yes.
So yeah. So anyway, so is there anything else? Perhaps then we could.
No, I don't
Okay,
think.
so we thank Professor Arnab Kumar Ray for these wonderful 5 sessions, and I hope the participants have enjoyed and learned a lot related to polarization optics and their applications in quantum communication. Thank you, Professor Arnab Ray.
Thank you very much.
So now we can have 5 minutes break before we start the next session.
All right, all right. So then I'm logging out. Then I have no.
Yeah,
I mean,
sure.
yeah, okay,
Thanks.
okay.
Thanks
Thank
once
you,
again.
thank you, thank you.